Hey, I remember that. Oh, I found that on the ground when you left yesterday. Okay, so how good are measurements? Okay, so when scientists are talking about how much they trust their measurements, they use a couple of different words. It's two different words. Okay, the words they use to describe, we tend to use interchangeably, but they mean different things. Okay, the first one is accuracy. How accurate something is. And accurate means how close it got to the right value. Did you get the right answer? If something's accurate, you got the right answer. Is that what you thought accurate meant? Okay. So not a new definition of the word. Right? This is what you expect accurate to mean. Okay. Closely related, but not the same thing, is precision. What does it mean to be precise? Well, to be precise means that you can repeat that same measurement. And the degree to which you can repeat it. How close together are your measurements? Which do scientists want? Accuracy or precision? The answer is both. Okay? It's both. You need both. Because you want to be able to get the right answer and you want to be able to get it again and again. You want the measurements you take to be the right number, and you need to do that every time, so it needs to be repeatable. I want the right answer and I want it over and over again. So if you'll notice, the difference between these two is what they're comparing to. Accuracy compares to the right answer. Precision compares to the other answers. Does that make sense? I've got some brown paper towels right here. Hey, so the book used a dartboard analogy. I'm going to use a golf analogy. Okay, so first shot goes there. Second shot, there. Third shot, there. Was this golfer accurate? No. Were they precise? Yeah. So inaccurate but precise. Did the same thing wrong over and over again. Is that a good way of describing it? That's how you get inaccurate but precise. You do the same thing wrong over and over again. It happens really often with a ruler because people measure from the end of the ruler to there. But if you look carefully, lots of rulers, the end is not zero. They've moved it in a little bit. So if you use that ruler the same way every time, you would get the same answer every time, but it'd be wrong every single time. Okay. Second hole. First shot goes there. Second shot goes there. Third shot goes there. Were they accurate? Okay. Fact is, they're more accurate than you think. Because when we got multiples, we want to talk about the average number, right? Where's the average of where those shots went? It's practically in the hole, right? It's right in there. It's about the middle of that triangle, right? So you got a bunch of them. You talk about how accurate the average one is. Hmm? Were they precise? Yeah. Yeah. If only I golfed that well. Hey, next shot. It's my golfing. First shot. Second shot. Third shot. Were they precise? No. Were they accurate? Maybe. Because where's the middle of that? The middle's right in here. That's better than you thought. Okay. Would you trust this golfer? On average, I'm in the hole. No. This is not good. You wouldn't trust those numbers because they're too spread out. So you wouldn't trust that average. You got the accuracy, but without precision, so you don't trust that answer. That makes sense? You did different things wrong every time here. Okay. And then the next hole. Was it accurate? Was it precise? We can't say. How come we can't say whether it was precise or not? There's only one, right? So if there's only one, you can't talk about how close it was to the other shots. Okay, make sense? Okay, so we're not going to do it with golf shots. It's going to be with numbers. Okay, so 3 students measure this room to how far across it is. The first one measured as 10.2, the second one 10.3, and the third one 10.4 meters. Were they precise? Those numbers are pretty close together. Less than 1% difference between them. All right, so those are pretty close together. Were they accurate? We don't know. How far is it across the room? Well, I don't know, but if you had to guess right now, what would you guess? Use the stuff on the screen. If you had to guess, what would you guess? 10.3, the average of those, right? Given that data, if somebody asked you, the most you know right now is 10.3. That makes sense? And you're fairly trusting because measured 3 times, they're pretty close together. Although just measuring across a room, if you're off by 1/10 of a meter, you're off by that much. That's pretty far to be off, isn't it? You expect to do better than that. So they must have had really lousy equipment. Does that make sense? So, okay. So accuracy can be true of an individual measurement, or if there's several, you talk about the average of the measurements. So if I take 1 shot, I can talk about whether it was accurate or not. If I take 5 shots, I take the average of them and talk about whether the average is accurate. Precision requires several measurements before you can say anything about it. You can't say how close the numbers are together until you measure it more than once. Seems legitimate. Okay, so we have 4 combinations possible of good and bad accuracy and precision. Okay, if you have good accuracy and good precision, that's great data. If you've got good precision but bad accuracy, you're doing the same thing wrong all the time. If you have bad precision and bad accuracy, you're doing things really wrong. But think about this case. There's a special word for the situation where where you're accurate, but you're not precise. Anybody know the specific word that describes when you're accurate but not precise? Well, translate that. You're accurate, you get the right answer. Not precise, you can't get it again. I heard it right there. The scientific term for that is lucky. You got the right answer, but you can't get it again. That's lucky. And luck is not what we want to count on. The one that's going to mislead you is the precise but inaccurate. Because you're not going to notice it's wrong. It's going to look like really good data. All the things are really close together. But you won't know it's inaccurate until somebody tells you what the real value is. Make sense? Okay. So it's a pretty simple concept. as long as you say, what am I comparing it to? Am I comparing to the right answer or the other answers? That's the difference between accuracy and precision. Okay. All right, so now for something that you're going to complain about all year, because I'm going to talk about it all year. Significant figures. I'm going to talk about it so much, I'm not going to say significant figures. I'm going to say sig figs, because I'm too lazy to say significant figures every time I need to. In fact, it is on your papers, you're going to see a scroll that looks like that. SF. It's telling you, while your answer may be right, you've got the wrong significant figures. Significant. Something significant, it's meaningful or important. Right? Figures, they're talking about numbers. So it literally translates to important numbers or meaningful numbers. They're the numbers that actually mean something. We're talking about the situation where you do some math on your calculator and you get a screen full of numbers. Where do you round it off at? Okay. Well, the answer is you round it off where the numbers are meaningful. So we have to look and see which numbers mean something. And this is all based on measurement. The reason why we have this technique that you don't use in your math class is because your math teacher doesn't have you measure stuff. They're not using measurements, they're using perfect numbers. Okay? Well, the rule for scientists is we trust your judgment. We trust your judgment. That when you're looking at a ruler, we expect you to put one more decimal place than there are lines on the ruler. Let me show you, and you do it automatically. Once again, we're talking about something you do automatically. Okay? But now we're just saying you have to do it every time. And that you have to assume that other scientists are doing the same thing. Here's a simple example. Okay, how long is the green bar? Would anybody say 4? No. Would anybody say 5? No. You'd say 4.5, 4.5. Are you sure it's exactly 0.5? No. But you know it's not 0.2. Okay? So that 0.5 has meaning even though we're not sure of it. We know that whatever it is, it's close to 0.5. It might be 0.4, it might be 0.6, but it's close to 0.5. You do that automatically, right? Okay. So what happens when I change rulers? I go to a ruler with more lines on it. Okay. Would you still say 4.5? No, because 4.5 is the line, right? Okay. So 4.5 is the line. So this is a little bit past. It looks like it's about halfway past. So 4.55. So notice that the ruler has 4.5. I can read those lines, but I have to go one place further. And you have to say that all the measurements in chemistry, they've done this for. Everybody treats numbers the same way. Okay? If I don't know that last one's a 5, do I have any idea what number's behind it? I have no idea what's behind that second 5, do I? Okay? So the better the marks, the better we can estimate. So the estimated number is meaningful. And the scientists have agreed this is how we're going to work out that last digit is estimated. Everything bigger than it, we know for sure. So the significant figures are all the numbers we know for sure and one we've estimated. So the last number is an estimate. Okay. Okay. So this is going to change our worldview. You're used to looking at the last digit's an estimate. Question?
Yeah, I was going to say, even if it's like directly on.
Okay, so then you would put 0.0. Does that make sense?
Yeah.
Yeah. So because you say, oh, it looks like it's right on the line, but I'm not absolutely sure. Okay. Someplace between 0.9 and 0.1 is what we're saying when we put 0.0. Okay. So now it works backwards. The measurements we write down tell us about the ruler we measured with. But you saw the two rulers. One of them I could write 4.5. The other one I could write 4.55. I added another line on my ruler so I could add another decimal place. So when I see two decimal places, I know the lines are at the 1/10. When I see one decimal place, I know the lines are at the ones place. That the numbers we write down tell us about the ruler. We're used to using rulers to find numbers. Now the numbers tell us about the ruler. That's kind of strange. Okay? So whatever that last digit is, it's in between the lines so that you know that the lines are in the 1/10 place bigger. So what is the smallest mark on a ruler that measures 142.13 centimeters? What does the ruler look like? If this weighs 142.13 centimeters, is there a line every one place? That ruler wouldn't do that job, would it? That looks like 0.1, 0.2, we're not sure, right? Would that ruler do it? Okay, so see how this number told me I was using that ruler. Makes sense? And it's not just rulers, it's all measuring devices. The last one's estimated. Ruler's just the easiest one to show you. Okay? So describe the ruler where somebody wrote down 142 centimeters. What does that ruler look like? Okay. So on 142, what's the estimated number? The 2 is estimated. So that means I'm sure that that's a 4. So that means there must be lines where the 4 is at. And the lines are in the tens place, right? Everybody see how that says 142? A line every 110, 120, 130, 140, 150. So in the tens place. Okay. So since I saw 142, I knew the ruler had to look something like that. What about 140 centimeters? Does that say 140 centimeters? Or does that say 140 centimeters? Can you see where our dilemma is? I just said that the ruler, the number told me about the ruler, but now this number talks about two rulers. Well, the problem is the 0. Is the 0 significant or not? That's our question. Because there's two ways to get a 0. A 0 can be an estimate, it looks like it's right on the line, or the 0 can be a placeholder. Right? So 0 can do two jobs. So we have to decide when I put a 0 there, which of those two rulers am I talking about? Did you ever see that? That's why you did all those things about zeros on the reading guide. It was about rulers. You got to differentiate between these two rulers. Okay. Okay, so we need a set of rules for zeros. Okay, everybody comfortable with that? We don't have any question about the 1 and the 4. If it's a non-zero, it's significant. The question is which zeros count, which zeros don't. Okay, because everything that's not a 0 is going to count. So which zeros don't count as significant figures? There are 4 places zeros can show up. 2 of them count, 2 of them don't count. Those at the end of a number before a decimal point don't count. Those zeros at the end. They don't count as significant figures, but they have to be there as placeholders. If the number is smaller than 1, that means it's going to start with a decimal point, 0 point. Any zeros before the first non-zero are going to be insignificant. It won't count as significant figures. The zeros in front of 0.045. In both cases, those numbers are placeholders. How can you tell if they're placeholders? Well, if you move the decimal point, you change the value by 10. By exactly 10. That tells you it's a placeholder. Okay, if I move here, it's exactly a 10. Here, if I got rid of that, if I move that decimal point to here, I'd be multiplying it by 10. It's exactly 10. Those are placeholders. Anyone where we move the decimal point, it would change the value by a multiple or multiplier dividing by 10. You okay with that? Those zeros are placeholders. Those are the 2 places they don't count as significant figures. They're just there to make sure the number's the right size. Because 124 and 12,400 are not the same value. Yeah. Okay, so those zeros are only placeholders. Which ones do count? Zeros in between other significant figures count. Zeros in the middle count. A 1,002. If I move decimal points here, or if I get rid of those zeros, I'm not changing it by exactly 10, am I? 10 times 102 is not 1,002. So those zeros aren't placeholders. You think about it, if I got this 2 here, I know it's significant, right? I know it's significant. So that means it's last, so it's estimated, so I have to be sure of these numbers. If the 2's the estimate, the other ones I'm sure of. Okay? And zeros at the end of the number after a decimal point count. Zeros at the end of the number after the decimal point. Because if I got rid of those zeros, I wouldn't change the value of the number at all. Right? It'd still be the same number. Doesn't change at all, so it doesn't change by tens, it doesn't change at all. Those aren't placeholders. Fact is, they don't need to be there to do any math, so they wrote them in for a different reason. They wrote them in to tell you if that's an estimate. And then I'm sure that's really a 0. So it looks like it's on the line between 45.8299 and 45.8301. It's in between those two numbers. But it looks like it's right on the line. Okay. So, holding places they count. They don't. If they're holding places, they don't count. If they're measured or estimated, they do count. So, ones we're sure of and one estimate every time we write down. So zeros show up in 3 places. At the front, they never count. In the middle, they always count. And at the end, they sometimes count. If it's a big number, they're not going to count. If it's a small number, they will count. If it's before the decimal point, they don't count. If it's after the decimal point, they do count at the end. Okay. Right. So, here's our 142 different ways. Which one of these says 140? Okay. Well, if I write 140, according to the rules, does that 0 count? No, it does not count. That 0 does not count as a significant figure. So if it doesn't count, then the estimated number is the 4, and I'm sure that there's a 1. You okay with that? So that means it's the one that has the lines where the 1 is at, in the hundreds place. When I write 140, I'm talking about the bottom ruler. Okay? So 140 describes the bottom ruler, not the top ruler. Because the top ruler, you'd want to say it looks like it's right on the line. Okay? So somehow, I need to talk about that top ruler. I need to say it's on the line. I got to make that second 0, make a 0 count. Yeah. Yeah. So the way we make zeros count is decimal points. So we're going to talk about that in just a second. So we do have to be able to talk about that top ruler, and it's going to involve decimal points because the 0's at the end. Right? The 0 at the end counts half the time. It depends on whether there's decimal points or not. Okay. So 50 only has 1 sig fig. Everybody okay with me saying 50 only has 1 sig fig? The 0 doesn't count? Okay. But what if it really had 2? How can I write it down so I made sure that 0 counted? The 0 only counts if it's after the decimal point, right? So I have to write 50, but I have to put a decimal point here. Well, that's only 5. How can I write 50 with the decimal point there? Scientific notation. That's why one of the reasons, a third reason we're going to need scientific notation. What's the third reason? Because 5.0 times 10 to the first is still 50. It's got the same value. But now the 0 counts as a sig fig. We'll spend more time working with scientific notation later, but all we have to be able to do is get it into scientific notation by moving decimal places, right? So all I did is say, hey, there's 50. I need to make it count, so I move the decimal point once, so I have to multiply by 10 once to keep it the same size. I made the first number smaller, so I have to make the exponent bigger. I made the first number smaller, so I got to multiply by more 10s to keep it the same size. Okay? So that's that's the answer is you make the 0 count by getting it after the decimal point. So back to our 140, we said that that was 140, right? How do you write the top one? Well, it's the 140. It's the 140, but I need that 0 to be counted. I need to get that 0 behind a decimal point. So I'm going to change it so it's behind the decimal point. I'm actually going to move it twice to get 1.40, keep the 0. And I moved it twice, so that's times 10 to the second. Yeah.
You have only moved it once, or did you have to move it twice?
Moving once and getting 14.0 times 10 to the first would be okay. We're going to find that we usually want to get it down to a number between 1 and 10. So I'm going to do what scientists do most of the times, so you get used to seeing what they do. So get it to a number between 1 and 10. Because then, if you got everything to a number between 1 and 10, all you have to do is look at exponents to see which is bigger and which is smaller. Make sense? Okay. So, two rulers, I talk about them different ways. If I want to say that, if I want to say it's right on the line, because that's what it looks like, it's right on the line, I have to talk about that 0 as counting. And the only way to get a 0 at the end to count is to put it after a decimal point. So, let's count some sig figs. How many significant figures in 458? This is the easy one because there's no zeros, right? So this has 3 sig figs. 4,085. Okay, the 4, the 8, and 5 for sure. The 0 is between, so it counts, right? So that is 4 sig figs. 4850. The 0's at the end. If I crossed it off, it would change it by 10, a factor of 10, right? So that tells you that's a placeholder. So this is only 3 sig figs. How many people say 3? People say 4. Okay, so we got some divide. So the 4, the 8, and the 5 for sure. Where's the 0? The 0's in front. There's 2 ways to get this right. One is to remember that 0's in front never count. The other is to cross off this 0. Changes by a factor of 10, right? That would be making it 10 times bigger. That tells you that 0 is a placeholder. So it's only 3 sig figs. 0's in front never count. 0's at the end count sometimes. There's lots of 0's. The ones in front didn't count last time, so they're not going to count this time. The one in the middle counted the first time, so it's going to count this time too. So that's 4 sig figs. And okay. It's not supposed to be a trick question. It starts with a 4 and ends with a 5. All the 0's are in between. Right? So they all count. Because they're in between other significant figures. They're not in the front, they're not at the end, so they all count. So that is 8 sig figs. Because they all count. Because they're between the 4 and the 5. And people say 2, 3, 4. Okay, so we got 3 and 4 again. So the 4 and the 5 count. This 0 in between. This 0, oops, I gotta get that so it stops doing that. This 0 at the end and crossing off doesn't change the number at all. It's not a placeholder. So it counts. It's 4 sig figs. If you think about it, what would the ruler look like? This would be exactly on 405, between 405.1 and 404.9. Looking like it's right on the line. Okay. Whoops. How many in 40, 50? And people say 2, 3, 4. All right, so it's not 4 this time because the 0 is a placeholder. If I cross it off, I change it by a factor of 10. So it is a placeholder, so it doesn't count. Placeholders don't count. So this would be 3 sig figs. Two, 3, 4. Yeah, this 0 doesn't count. It's not a placeholder. This 0 doesn't count. So this one, zeros in front never count. At the end, they count if they're after the decimal point. This one's after the decimal point. So that is 3 sig figs. It's not a placeholder, right? And people say 3, 4, 5, 6. Yeah, because the 4's in front, the 5's at the end, right? Everything in between. Now you can. So, got zeros in all sorts of places, right? Okay, so this 0 at the end after the decimal point, it counts. These 3 zeros in between, these zeros in front, right? So that gives us our 6 sig figs. It's a little strange, but it's going to be something to get used to doing. Okay, so you're going to have to round off the right number of sig figs. The book talked about a different method of rounding. It's a very rare thing that you run into. I'm not going to worry about it. Okay, but what it is if your last digit is exactly a 5, and there's nothing trailing behind that 5, you should round up half the time and round down half the time. That's what it's about, because if you round up every time, you're rounding up too often at the 0.5. 0.5 is exactly in the middle, so it should be half up and half down. So that's why they do the number in front of the 0.5. We don't have to worry about it, but it actually makes it so you don't, otherwise you round up a little bit too often. Okay. So the rounding rules look one number behind the one you're rounding. If it's 0 to 4, don't change it. If it's 5 to 9, make it 1 bigger. Are these rounding rules different than you've heard before? Okay, the difference is we're going to round to the right number of significant figures. And we may have to put some placeholder zeros in. So, round 45.462 to 4 significant figures. Okay, I start with the biggest non-zero, which would be that 4, and there's 1, 2, 3. The 4th sig fig would be the 6. Behind that 6, there's a 2. What do I do if there's a 2? Don't change it, so that would make this 45.46. Okay. Round it to 3 significant figures. Well, start with the 4, the 5's the second, the 6, the second 4 is the third. Behind that 4, there's a 6. I round up, so I get 45.5. That's not rounding any differently than you've done ever before, right? Round it to 2 significant figures. Okay, here's the mistake people make. They say, oh, 45.5 goes to 45.6. But no, we're not trying to round 45.5. We're rounding 45.462. You don't round before you round. Okay? So the second sig fig is the 5. Behind that there's a 4. So I leave it alone. I don't round it up to a 6. Okay? And to one significant figure. Okay. People want to put 5 as an answer. If I owed you $45.462 and I said, let's round that off, here's $5. Would you accept $5 as payment? No. What's missing? The placeholder. At 4 is in the tens place. I've got to keep it in the tens place. So I have to put the placeholder in. Make sense? Because 50 is about the same size as 45. So sometimes you have to put the placeholder zeros back in. So, round 3.45789 to 3 significant figures. And write it down on your paper, just so you can check to see if you're doing it right. Make a commitment. Hey, you should have gotten 3.46, because the third sig fig is the 5. Behind that 5 is a 7. Okay. So that's what your homework will have you do. No big surprises. Yeah. Okay, nice. So you didn't leave it at home. You left it here on the floor. Have a great one.